Okay, now, excuse for the hoarseness and coughing. The workflow for building network models is very straightforward. The first thing you want to do is define the types of cells, the cell classes that are going to be in the network. The second thing you do is to create the instances. That is, of each cell class, how many do you get of this class, how many do you get of that class, et cetera, et cetera. And the third thing you do is you connect the cells, okay? Whoops. But we're going to just focus right now on what it is that makes network models even possible, okay? So we need to talk about communication between cells and how that is set up. Well, generally speaking, communication between cells that is synaptic or pseudosynaptic can be regarded in two categories. One is gap junctions, the other one is chemical synaptic transmission, which would be graded or spike triggered, depending on the synapse in question. We're going to focus on graded synaptic transmission, and for the moment, we're going to focus on synaptic transmission, not gap junctions. And let's start by looking at graded synaptic transmission to begin with. And the physical system would be some presynaptic variable governs continuous release from the presynaptic terminal. And this transmitter diffuses across a synaptic cleft where it binds to receptors that ultimately modulate some postsynaptic property, okay? And the abstraction that we use in most computer models is that there's some synaptic conductance attached to the postsynaptic cell, to a segment on the postsynaptic cell, whose numeric value is some function of membrane potential in a segment of the presynaptic cell. Well, when you instantiate a model cell, automatically every segment knows the membrane potential of its own compartment and can discover the membrane potential of its adjacent compartments. That neuron takes care of that automatically. But how can you with neuron tell something in one segment about something that's going on in some other segment that isn't adjacent? Okay, so how does the postsynaptic cell know what V-pre is? Well, you can use a pointer variable that links the postsynaptic variable to the presynaptic variable, and the syntax for that is that's done in NModel, where you declare in the neuron block that your NModel specification of the synaptic mechanism, which is going to be attached to the postsynaptic cell, has a pointer variable, and when you set up the connectivity, you're going to need to associate that postsynaptic synapse the thing that's attached to the postsynaptic segment. You're going to have to attach that pointer variable to the variable in the presynaptic compartment. And this is how you would do it with Hoke. I have some example of how to do it with Python, but we're going to skip over that because we're going to focus on spike-triggered synaptic transmission because most models we're dealing with are spike-triggered. Not to say you can't do it with Python, not to say it's more obscure than the Hoke, just that it's off the topic for the rest of this presentation. Okay, so let's think about the physical system here. In a real network in which you have a presynaptic cell that projects an axon that synapses onto a postsynaptic cell, you've got this axon, and it can be quite long. And what you're doing is you're modeling the presynaptic cell, calculating membrane potential, throughout the presynaptic cell. And when a spike finally is triggered, wherever it originates from, whether it originates in a dendrite and enters the soma, whether it originates in the soma or somewhere in the axon initial segment, you're going to be concerned about when that happened. Our conceptual model is that the spike in the presynaptic terminal is important, and it triggers transmitter release. And the presynaptic details of what's going on in that presynaptic terminal aren't important. But we're going to have to simulate the time course of membrane potential along that entire axon, okay, if we maintain this detailed conceptual model. Okay, in the postsynaptic cell, our conceptual model is that there's a differential equation here or kinetic scheme here that is perturbed by the fact that a spike happened in the presynaptic terminal. Okay? So our basic idea is that we have a complete representation of the presynaptic cell, including propagation from the spike trigger zone through the axon to the terminal. And at the terminal, we attach a spike detector. And when the spike detector determines a spike has happened, after some latency on the order of a millisecond or so, typical synaptic latency is on the order of a millisecond or so, something happens to the conductance attached to the postsynaptic region. Okay? Well, we immediately can make our task more computationally efficient by assuming that propagation along the axon is reliable and always has the same conduction delay. And if we do that, we end up with a simpler situation. We only have to represent the presynaptic cell up to and including the spike trigger zone. And we attach the spike detector to the spike trigger zone. And then our delay that we interpose between detection of a presynaptic spike, a spike in the spike trigger zone, and the perturbation of the postsynaptic region is going to be the sum of conduction latency plus synaptic latency. Okay? So we've thrown out the need to deal with a whole bunch of equations because every compartment is going to include an ODE for membrane potential, an ODE for GNA, an ODE for GK, and an ODE for whatever other conductances, voltage-gated conductances are present. So we've saved ourselves a lot of storage and a lot of computational effort. Okay? And to do this, we take advantage of a thing called the NetCon class. Now, what does the NetCon class encapsulate? It encapsulates a spike detector and a delay and an event delivery system. Okay? And what happens what happens in Python, the way we set this up, is we create a new instance of the NetCon class with a statement like this. NC is going to be the thing that's going to refer to the new instance, is equal to h.netcon, and inside the parentheses, we have the name of the source, comma, and the name of the target. Well, what is the source going to be? The source is going to be a pointer to a presynaptic membrane potential, okay? And the target is going to be a synaptic mechanism that can receive events, okay? Because what is going to happen is during a simulation, every time the presynaptic cell fires a spike, the spike detector will detect it, and it will add an event to an event delivery queue where that event sits and waits until it is time to deliver the event to the postsynaptic terminal and perturb the postsynaptic mechanism. Okay? All right. Now, a NetCon has a number of ancillary parameters. We can include them when we first create the NetCon, or we can just create the NetCon that attaches the spike source to the target, and then we can add them later on. We can specify the threshold. The default for threshold is 10 millivolts. And that is the value of the presynaptic variable that we're watching, that when that presynaptic variable crosses that threshold in a positive going direction, that triggers an event. Okay? So this is actually a fairly strict criterion for a presynaptic spike. We're looking for a positive going threshold crossing that goes above 10 millivolts. The default value for the delay associated with the NetCon is 1 millisecond. It has to be non-negative. Okay? And if we're going to be dealing with network models that are distributed over multiple processors, it actually has to be greater than 0. Okay, the delay. But by default, it's 1 millisecond. And we have a NetCon weight, which is the strength of the perturbation. It's actually an array. The 0th element, the first element of the weight vector, is generally treated by the synaptic mechanism as a measure of how strong is the perturbation going to be. Okay? And what's the characteristic of our synaptic mechanism that receives the events? It needs to contain, its end model specification needs to contain a net receive block that contains statements that tell the mechanism, here's what you do when you receive an event. When an event is delivered to an instance of this mechanism, here's what the mechanism does. Okay, so where does that get us? Well, for one thing, it gets us efficient fan out. Because if we have a common spike source and multiple paths projecting to different synapses, we only need one spike detector watching that point, watching that spike trigger zone. And then we can have multiple NetCons watching that spike trigger zone. They're all going to use a shared spike detector, a point for reducing overhead slightly. And each one of those paths, each one of those NetCons can have its own delay and its own weight and target its own synaptic mechanism. And that synaptic mechanism could be on a different branch of the same cell or a different cell. Okay? Even more efficient potentially is convergence or fan-in, which often in the case of cells, you'll find that within an electrically compact region, there's more than one instance of the same type of synaptic mechanism. And since they're all of the same basic type, they all share the same local reversal potential, and they all have similar kinetics, similar dynamics. So they can all be described, if they are linear, if it's a linear ODE that we're dealing with that describes an instance of a synaptic mechanism like that, a single instance of that mechanism can handle multiple afferent event streams. So here's such a case. We have two presynaptic cells sending events via two different paths to synaptic mechanism, and we have a spike detector attached to this first cell's spike trigger zone, followed by a delay that then delivers events to this mechanism, which I'm not showing here by any little cartoon figures or widgets. And we have a second path from a second spike initiation zone with its own spike detector, might have a different threshold for detecting a spike if we wanted that. Certainly could have a different delay. And these two event streams can have different weights. And if they have plasticities, they can have their own local record of their own use-dependent plasticities, so that you can have stream-specific plasticity. Okay? All right. But the neat thing about this is that no matter how many paths converge on that single mechanism, only one bag of ODEs is required to govern it. So if we had 50 GABA A synapses attached to a cell body, think basket cells, in our network model, we only need one GABA A representation attached to the cell body, and it can handle 50 different afferent streams. And dealing with an event is extremely cheap because it involves just basically a few threshold calculations and a few algebraic equations and a few assignments. It doesn't involve solving an ODE. Okay, so we can achieve tremendous efficiency. We don't have to have 50 sets of GABA A ODEs to represent all the basket cell terminals on the soma, or for that matter, within a single segment, if there's multiple AMPergic attachments, they could all be handled by a single AMPergic mechanism. Okay, so good for efficiency. Let's look at a particular example. Here's an example. A synaptic mechanism that has a very fast rise time followed by a mono-exponential decay. Well, what is that called? Experimentalists think of this as when they think of AMPA synapses, because they have extremely fast rise time on the order of a few tenths of a millisecond, followed by typically a mono-exponential decay of conductance, which has a time constant on the order of 3 to 5 millisecond time constant. So here is the skeleton of an N model specification for such a mechanism. Notice we give it a name, it's a point process. Notice it has 3 range variables, 2 are parameters, and 1 is an assigned variable, the non-specific current. We're not keeping track of the chemical effect of opening this synapse. We could, if we wanted to, we could redefine this as U-zion something or other, but we're just using non-specific current for this, okay? I'm leaving out all of the ordinary variable declarations, et cetera, et cetera. Now I'm including only the key N model blocks. An initial block that says that when this synapse is first initialized, its conductance is 0. It's off. The breakpoint block, which says, where's the bag of equations that we solve? Where's the ODE that we solve, and what method do we use to solve it? And then how do we calculate the current generated by this thing? And the breakpoint block really should be called like the currents block, but for historical reasons, it's called the breakpoint block. But this is where you put equations that calculate a current, okay? That's generated by your mechanism. All right? We have a derivative block which says what happens to the synaptic conductance. Well, if this synapse doesn't receive an input, what happens is the synaptic conductance decays mono-exponentially from whatever its initial value is. If it starts at 0, it ends at 0. But what happens if it receives an event with a particular weight? Well, what happens is that at that instant in time, the synaptic conductance is perturbed by adding the value of the weight to G. And after that, the conductance resumes its mono-exponential decay. Let's take a look at that. Here we have a synaptic mechanism attached to a postsynaptic cell, and we have 2 different afferent streams driving it. One afferent stream has weak weight, a low value for weight. That's indicated, the times of the events on this stream are indicated by these red markers, okay? And another stream has a strong weight. It has a strong perturbation of this synaptic mechanism. So every time there's a presynaptic event delivered to this via this stream, it produces a bigger perturbation of G. So a weak event occurs, a millisecond later, we get a small perturbation of G followed by mono-exponential decay, get the big perturbation from the other stream, a bigger jump of G. Now if we have overlapping event streams, we see that the conductances summate appropriately, and when they're both occurring simultaneously, we get a much bigger perturbation of G, and when the strong ones are happening all by themselves without the weak ones at the same time, we get a smaller perturbation of G. And we see that membrane potential in this postsynaptic compartment behaves as it should. You get temporal summation of membrane potential. All this works well because this is a linear synaptic mechanism, and this superposition, because it's a linear ODE, and the superposition principle holds. Okay? All right. So this is our breakpoint block, just to remind you, our derivative block and our net receive block. Just to remind you, that's what's going on that causes G to jump like that, okay? All right. Well, what about more complicated things? Can we get a use-dependent synaptic plasticity, like, for example, facilitation? If we had, well, this envelope of waveforms shows what would happen if we had a single event, a unitary activation of this particular synaptic mechanism, okay? If we did that, the response would follow this trace and it would just decay away like that. You'll notice we have a bioexponential time course. So this is time course governed by 2 ODEs, okay? But if we paired that conditioning pulse with a test pulse later on, we would see some potentiation. So this is what would happen if the interval between the conditioning pulse and the test pulse is long. We get this initial perturbation, which reaches 1 nanosiemen peak conductance, and it decays away, and we don't see too much synaptic conductance anymore, but something in this synaptic mechanism remembers the fact that a previous event had occurred, and it gives us a bigger response on the second activation. And if we moved the activation of the test pulse, we moved the time of occurrence of the test pulse closer and closer and closer and closer to the conditioning pulse, we would see this envelope of response amplitudes. And we get to a point where it reaches maximum, potentiation is maximum, because we're assuming the potentiation process has its own time course. And its own time course is bioexponential with very different time constants from what governs the unitary response. So the potentiation envelope needs to have its own 2 time constants. How can we do that, and how can we do that efficiently? This code does it. Here are the 2 equations that govern the mono-exponential response. Okay? 2 mono-exponentially decaying variables, and the difference between them gives us this envelope. What happens when a single event arrives? Well, initially, this thing has no history of being activated, so all these variables are set to 0. If a new event arrives, this potentiation variable and this potentiation variable are updated according to their own dynamics. These are the variables that have mono-exponential time courses that govern this envelope, this potentiation envelope. But notice we don't have to solve these numerically. We can use their analytical solutions because we know the last time they were activated, and we know the values they had the last time they were activated. And knowing that information and knowing the analytical solutions to the ODEs that govern them, we can calculate their values at the current time by simply applying the mono-exponential decays that each of them suffers from its previous value. Cheap computation. No numerical solution of ODE needed to manage G1 or G2. So we've updated G1 and G2 to the time of the current input. And now we do the thing that potentiates G1 and G2. We increase G1 by whatever the factor is supposed to be, and we increment G2 by whatever factor it's supposed to be. We reset the time of the most recent activation to the current time, and we figure out what should the effective weight be. So we calculate this value of W from the nominal weight, okay, which you used when you set up the NetCon in the first place, and you say, okay, when this thing is naive, it's going to have a weight equal to this numerical value, okay? which is the first element of the weight vector. And then when it's activated in the future, it'll be that first element of the weight vector times 1 plus the difference between these two mono-exponentially decaying terms that govern the potentiation envelope. Okay? And we keep track of them. We save W in the weight vector, and we save G1 and G2 in the weight vector, and we save T0, the time of the most recent activation, in the weight vector. So you didn't even consciously do anything about these things when you set up your model. You just connected the presynaptic spike source to the postsynaptic mechanism using a NetCon statement. The only element in the weight vector that you specified was this first element, and all these other elements are initialized to 0 because it's a naive synapse. But as soon as it's been activated, it has history. And once it's been activated once, that history is stored in the weight vector for reuse the next time it gets activated. So this is how we get a synaptic mechanism that has complex potentiation, depotentiation dynamics at no additional computational cost. The cost to execute this bit of code and to save this data in the weight vector is nil compared to the cost required to solve these two ODEs. Okay? Really slick. Also, you can have associative potentiation, like spike timing dependent potentiation. We're not going to talk about that in this presentation. Okay, let's talk about artificial spiking cells. Notice that this net receive block is only executed when a new input event arrives. Okay? So all this computation can happen, and all this nice dynamics can happen because we know analytical solutions to the ODE that governs these things. What if we have an artificial spiking cell? Most artificial spiking cells have simple dynamics, so simple that we know the analytical solution. Given the state variables for the artificial spiking cell at the current time, we can predict the trajectory of that cell's activation variable, which is, think, equivalent of membrane potential, and we can predict, is that cell going to spike? Or is it not going to spike? Analytically, we can do that in the net receive block. And we don't have to do any computation with a breakpoint block or a derivative block. If we have a cell whose dynamics is so simple and straightforward that its solutions are analytical, so that we know the future state based upon the current value of the state variables and can predict based on time alone, plug that into equations that we have analytical solutions for, we can make an artificial spiking cell. Okay? As long as all state variables are analytically computable from a new initial condition. And the solution of artificial spiking cells is many orders of magnitude faster than numerical integration. So you can have thousands and tens of thousands of artificial spiking cells without the overhead that's even needed to advance the solution for a single compartment biophysical model cell. So that event-driven simulation runtime is proportional only to the number of received events, and it's independent of the number of cells or connections or problem time, because the only time you have to do any computation at all is when one cell receives an event. If a cell receives an event, that's the only time you have to do any updating of anything. Okay? If other cells are not receiving an event, you don't have to update them. And we can make hybrid networks that include artificial spiking cells and biophysical model cells. Very, very slick indeed. Here's an example of an artificial spiking cell, a leaky integrate and fire cell. A leaky integrate and fire cell sits quietly until it's perturbed. If it gets an excitatory input at some particular time, what happens is that its membrane state variable, think analog to membrane potential, is perturbed by an amount proportional to the weight of that input. After that, it decays mono-exponentially with time until it receives another input. In this case, another weak input on the blue stream here. Just update M. Mono-exponentially decays until it receives another input, in this case a strong input, an input with a strong weight, represented by this event in the strong stream, which brings it almost to spiking threshold, but not quite. Spiking threshold is 1, resting is 0. After that, it mono-exponentially decays until it gets another input, which is strong, so it jumps up high. And finally, at this point, it gets another strong input, which would drive it above 1, but instead we reset it, state variable to 0, and we generate an output event that gets delivered to every NetCon that's watching this integrate and fire cell. How many computations were necessary to do this? Only the updates involved at these points, really. And at this point, we don't actually really have to do this updating in between of showing the decay of M. We don't have to, because we know if we're starting out here, it's going to mono-exponentially decay. And if the next event never arrives, we don't have to update this thing's M at all. The only time we have to update M is if it receives an input event at some time in the future, and then we do a calculation here. At this time, the first calculation we do is to update the value of M based on what it had been before and what its dynamics are, which we know from the analytical solution. Simple algebra. Here's an example of the net receive block for this artificial cell. You'll notice in the neuron block, it's declared as an artificial cell. It's a class name because we might want many of these. It has 2 range variables. One is time constant, so each instance can have a different time constant, and one is M, because we might want to discover the value of M. Okay, we might want it exposed to us for diagnostic purposes. Okay? We don't actually have to expose it. If we want, we could leave it out, but well, when you're developing code, you might want it to be exposed. Okay, our initialization is that M is 0 at time t equals 0. And here's the net receive block. It doesn't have a breakpoint block. It only computes stuff when it receives an event. It receives an event with a weight W at a particular time. First thing that happens is it calculates the value of M at the current time based on what it had been in the past and the amount of time that has elapsed since it was last activated. Then it updates the time of the most recent activation, and then it calculates the value of M after the perturbation is added. So we add the weight of this associated with this event to M. We check to see if M is bigger than 1, in which case, we're above threshold. We generate an output event, which is picked up by all the NetCons that watch this particular instance of this particular class, and we reset M to 0. That's all the code that's involved. Super simple, computationally incredibly cheap. Okay? I'm not going to go into the details of each of these mechanisms. Neuron has basically 3 built-in artificial spiking cell classes. Many, many more are possible. INFIRE 1 is described by a single mono-exponential decay. It's exactly what we were just looking at. Okay, and this is what its graphical interface looks like. And you can see that in the point process manager, because the point process manager automatically treats artificial spiking cells as if they were, you can manage them. You can create instances of them with a point process manager. So it has a time constant. It has a refractory period, which we didn't talk about, but after it fires a spike, that's how long it remains unresponsive to further inputs. Okay? And there's its state variable M that it reports. INFIRE 2 has different dynamics. The assumption here is that in an INFIRE 2 cell, there is an integration that's going on, and it integrates a current. And what is that current? Well, there's a current that is governed by a steady state value, has a bias value, that's this IB, and it has a mono-exponential decay that lets it decay back to that steady state value. And that mono-exponential decay is governed by this time constant, tau s. So when an event arrives, this current may start out as a non-zero value. When an event arrives, the current is bounced up by whatever the weight is associated with the NetCon. If it's a positive weight, it's an excitatory input pushing the cell towards spike threshold. If it's an inhibitory event, it would have a negative weight and it would pull it away from spike threshold. And then after that, this current decays monoexponentially. This current is integrated by a first order integrator. Think of a resistor in, think of a resistor in parallel with a capacitor, okay, whose time constant is 10 milliseconds, okay? And we see here that when we start the simulation, the state variable m starts at 0 and starts to charge up, and left alone, m would eventually reach 0.5 in a steady state if there were no input events, okay? But since an input event occurred here and it's excitatory, m charges up even faster. So that looks like an EPSP. If the weight of an input event was negative, m would go in the other direction, and that would be like an IPSP. So this is a little more complex. The INFIRE 4 is described by 4 time constants because it allows you to have an excitatory current that has monoexponential decay, instantaneous rise, and an inhibitory current that is governed by 2 time constants. So there's our excitatory current decay time constant, 5 milliseconds by default, and the inhibitory current's 2 time constants, which govern the inhibitory current's envelope. You'll notice it looks more like a GABAergic event, okay? And these are integrated by a membrane that has a time constant of 50 milliseconds, okay? And so if we activate the excitatory all by itself, we'd get this value for m as a function of time. If we excited the inhibitory by itself, which we would do by having a NetCon with a negative weight, NetCon with a negative weight is treated as an inhibitory input, and that would give us that envelope for the membrane state variable. Okay, this is the envelope of the inhibitory current, and that's what you get when you filter that through a first order filter, okay, linear filter. So those are this is the most biophysically plausible seeming one, INFIRE 4 is. And again, it's all because these equations are analytically solvable and it all works very nicely and very fast. Okay, so how do we define the cells when we're building a network? We're going to use artificial spiking cells, or we're going to use biophysical model cells. They're going to be encapsulated in classes. Our artificial spiking cells are automatically encapsulated in classes. If we're going to be using biophysical model cells, we're going to be either using something generated from a cell builder or a network builder, or we're going to be writing something in Python. And Robert's got a really nice example of this, how to define a cell class. So this is just sort of toy example stuff that indicates that we're defining a cell class, so that then we can go and use our cells. We create a list that holds all of our cells, and we iterate to produce as many cells as we want, okay? And for each one that we create, we append it to a list, okay? That's the list that holds all of our cells. If we had a different type of cell, we'd do a similar thing for that different type of cell. If this was a pyramidal cell, we might say this would be for I in range n, cell equals pure, open close parens, then it would be pure cells dot append cell, okay? And we would have had a list called pure cells or pure list or whatever you wanted to call the list, okay? So once we've got our lists, we can calculate, or we can decide how we connect them. I'm not going to get into that. Robert, I think, has an example for that in his presentations. And I think I just want to get out of the way so that people can have lunch. Okay, are there questions at this point? Let's see. Questions, can we use NetCon weights? When you're dealing with biophysical model cells, do not use negative NetCon weights. Robert said flat out, don't. That's only true when you're dealing with biophysical model cells and a biophysical model synapse. Don't use negative weights with a biophysical model cell, okay? The only time you're going to use negative weights is when you're dealing with artificial spiking cells, okay? And why would you use artificial spiking cells? Because you can use artificial spiking cells to create a network that produces a synaptic milieu for your cell, as if it were in a slice or in situ. What is IEF? Exponential IEF. Is there, if there's a thing, okay, yeah, well, exponential, okay, is that a name of a particular bag of equations that somebody has implemented? And we can find a paper. Oh, Gersner and Brett, okay. Maybe so. I should look at that and see. I'll need a better, it's like a QIF, but worse. Is this a nasty bunch of equations, or is it worse in terms of performance? Well, we'll have to look at that and see if it's convenient to do, and maybe it can be done. Quadratic integrating fire, but even more nonlinear. Well, we'll have to look at that and see if it's possible to do that. I warn you that when you look at ModelDB and you look at Bill Litton's models, a lot of them use very sophisticated artificial spiking cell classes that involve a lot of verbatim C or C++ code. And you got to watch out when you're reusing Bill's code, because unless you know what you're doing, well, his require more study before anybody uses them. Okay, I have nothing more to say at this point, and I think we should break for what remains of lunch or dinner. We will resume, when do you want to resume? At quarter after the upcoming hour? Or do you want to resume at the actual upcoming hour? Do we see votes? I think if we resume at quarter after 15 past, because everybody is assuming that, that's what the schedule says, 15 past. So very good. See you all in 45 minutes. I'll be going away for a little bit, but I'll be back. And if people have questions, I'll be glad to answer them in the chat or whatever. And I assume Robert will be around also. So, alrighty. Bye-bye.